All right, today we're going to pick up on the notes on basic derivative rules. I'm going to avoid doing proofs this time, and some of these derivative rules we'll just avoid having proofs for, and we'll just accept them as truth. If you wish me to do a proof in class, I'm more than happy to. But yesterday, or in the last notes, we learned that if we take the derivative of x to the n, then we would get n times x to the n minus 1. Drop the exponent down in front, decrease the exponent by 1. Now this is the constant multiple rule, and it says if you have a constant in front of this expression, and really it's a constant in front of any function that you're taking the derivative of, then all that happens is the constant goes along for the ride. You can see the derivative of x to the n is n times x to the n minus 1. With that piece of knowledge, taking derivatives is going to be a very quick process. The derivative of y with respect to x. The derivative of x squared is 2x, and the constant goes along for the ride, so 3 times 2x is equal to 6x. Next one, the derivative of s is s prime of t. The derivative of t cubed is 3t squared. And then the constant goes along for the ride, negative 5 times that derivative, and we get negative 15t squared as our derivative. On the next one, we have 6 root x, and as you remember, radicals can be expressed as fractional exponents. So if I write this as a fractional exponent, the power rule can be applied. The derivative of y with respect to x. If I take the derivative of x to the 1/2, I'm going to get 1/2 x to the negative 1/2. And the 6 goes along for the ride. And this will simplify. 6 times 1/2 is 3, and x to the negative 1/2 is radical x in the denominator. Okay. Very often we have expressions that don't look like exponents or power rule, but if we rewrite that expression, then we can see the power rule is applicable there. So the constant goes along for the ride, and then we apply the power rule on x to the negative 2, and we get negative 2x to the negative 3. And if we were to simplify this, we'd get negative 6 over x cubed. The next one, if we express this as a fractional exponent, we'd have 4x to the negative 1/2. Okay, so that's just rewriting it using algebra. When we do the calculus of taking the derivative, the constant goes for the ride, and the derivative of x to the negative 1/2, exponent drops down in front, and we decrement the exponent by 1. Negative 1/2 minus 1 is negative 3/2. If we were to clean this expression up, 4 times negative 1/2 is negative 2, and then divided by x to the 3/2, which would be the square root of x cubed. I need to make a little more space in the notes here. Okay, and the last one here using the constant multiplier, again rewriting this, negative 8 times x to the negative 4/3. So when we take the derivative of y, we can write as dy over dx. And constants go along for the ride, and then the derivative of this, negative 4/3 drops down in front, and we decrement the exponent by 1, we get negative 7/3. If we were to clean this up, we would have 32 over 3 times the cube root of x to the 7th degree. Oops, that's off the page. There we go. All right, moving on to the next rule, the sum and difference rules. This just says if you were taking the derivative of two things that are being added together, you can take the derivative of each of them separately. Likewise, if they're being subtracted, you can take the derivative of each of the functions separately. And this is easiest understood by just taking a look at one of these problems. Here I've got a string of functions being added or subtracted together to make a singular function f of x. The derivative of x cubed is 3x squared. The derivative of 5x squared is 5 times 2x. The derivative of 2x is, I'm going to write it as 2. Yeah, we'll just write it as 2. And the derivative of negative 7 is 0. And if we were to clean all of that up, we get 3x squared minus 10x plus 2. Okay? And this is going to be pretty commonplace where we've got things being added together. Please note, if they are being multiplied together, there is a different rule, and we will learn that, but not in this lesson. So part B, if we take the derivative, 5 times 2/5 is 2. Drop the exponent by 1. The derivative of x to the 4th is 4x to the 3rd. The derivative of 3x squared is 6x. And then the derivative of negative 1 is 0. As always, sometimes it helps to rewrite the expression before you take the derivative so that we can see those power rules. So when I take the derivative, 1/3 x to the negative 2/3 plus 5 times 1/2, or 5/2 x to the negative 1/2. If we were to clean this up so that it read a little more easy, we'd get 1 over 3 cube root of x squared plus 5 over 2 root x. I don't know if that reads cleaner, but I know when it comes to evaluating a function, it's easier for me to evaluate radical expressions than fractional exponents. Here in part D, we already have the fractional exponents in place. This last one I'm going to rewrite as 4x to the negative 1, because that's the same thing, and that'll make it so I can use the power rule. So the derivative of y with respect to x. 5 times 3/2 is 15/2. And then we decrease that exponent by 1. Okay. Negative 6 times 5/3 would be negative 30/3. And then subtract 1 from 5/3 and we get 2/3. And then the last one, 4 times negative 1 is negative 4. And then we decrease the exponent by 1. This is 15/2 root x minus 10 cube root of x squared minus 4 over x squared, if we were to clean it up. H prime of x is 6x minus 8x to the negative 3 plus 2 times 1/2 x to the negative 1/2. Right, so this was 4x to the negative 2. 4 times negative 2 is, oops, that should be a plus. 4 times negative 2 is negative 8. Subtract negative 8 becomes plus. Decrement that negative 2 by 1, and we get a negative 3 there. Likewise, the square root of x, we saw up here, the derivative is 1/2 x to the negative 1/2, so 1/2 x to the negative 1/2. If we were to clean up the derivatives, plus 8 over x to the 3rd plus 1 over the square root of x. And in the last one here, it looks like f of x is a fraction, but there's only a singular term in the denominator, so we can rewrite this as 8x cubed over x plus 4x squared over x minus 3 over x. And in doing so, when we simplify that expression, we have 8x squared plus 4x minus 3x to the negative 1. And now we have a string of functions that we can apply the power rule to. So our derivative is 8 times 2 is 16x plus 4 plus 3x to the negative 2, or 3 over x squared. Okay, and then finally the derivative of sine and cosine. And I'm not going to go through the process of proving it. I do have an example of how to prove it down here using a trig rule. However, I'll save that for the classroom rather than a video. But I will do an intuitive exploration of these derivative rules. So the derivative of sine is cosine, and the derivative of cosine is negative sine. So let's picture what this would look like visually. If I looked at the graph of sine of x and asked you, what is the slope at the origin? You might calculate the slope by drawing a tangent line at that location and saying that it looks like it rises a height of 1 over a distance of about 1 unit, right? Pi halves is 1.5, so maybe this is about 1. So the slope at the starting point, I'll write here, slope is approximately 1. If I asked what is the slope at pi halves, well, you would say, oh, this slope is at a maximum, so the slope is 0. Similarly, if I asked you the slope at this point, you might again draw a tangent line and calculate that slope to be roughly negative 1. Okay. Well, here's a function, the cosine function, whose value at 0 is 1, whose value at pi halves is 0, whose value at pi is negative 1. And so this function models the slope that we're seeing on this curve. And so that's a nice intuitive way of exploring the relationship between these graphs and why the derivative of sine is cosine. Okay? And you could do the same thing going backwards to talk about, well, what's the slope of cosine at the starting point? Well, it's a 0 slope, so our derivative better be evaluating to 0. Then the slope here is negative 1, so our derivative should evaluate to negative 1. And sine does not, but if we did negative sine, it would, and that's why that derivative is there. Okay? Now that's just kind of an exploration of those two things. A more formal proof would to actually use the definition of the derivative, and we're not going to do that in the video. But instead I'm just going to throw out a quick function here. F of x equals 3x squared plus cosine of x, and ask, what is the derivative? Well, we just learned that we can take the derivative of each of these separately. So the derivative of 3x squared is 6x, and the derivative of cosine of x is negative sine of x. Okay. Or if I had another function, s of t is equal to sine of t plus the square root of t, then you could find the derivative of each of these separately. The derivative of sine is cosine t, and the derivative of root t is 1/2 t to the negative 1/2. Whereas we're seeing very frequently, we can simplify that as 1 over 2 root t. All right, so that's where I'm going to close the notes for this section. A lot of details here will get discussed frequently in class, and you'll see them often as we dive into doing derivatives on a daily basis. So good luck, have fun. Thanks for watching.